Welcome back. This next video, part 2, continues on our initial Module 7 probability notes. In it, we're going to look at calculating probabilities for simple events. So, calculating probabilities, much like calculating percent, is looking at a ratio between two numbers. It's looking at the ratio between the number of desired outcomes relative to the total number of possible outcomes for an event. So if we think about rolling a dice, right, then we might be interested in what the probability is of rolling an even number after one roll of the dice. There are 6 outcomes that would be favorable, right? With the probability of rolling a 2, a 4, or a 6. So we've got 3 positive outcomes out of 6 total possible outcomes. And so as a decimal, that's a 50% chance. It's 0.5000. We're going to report our probabilities to 4 decimal places. Okay, so that they're consistent with calculations that we'll be doing later on, right? And so now what I would challenge you to do as an exercise is think about what if you rolled either a regular dice twice, or if you rolled 2 dice, what's the probability that the sum of the 2 dice rolls is 11 or greater? First, you need to think about what the total number of possible outcomes are, and then calculate the probability that the sum of the total rolls is greater than or equal to 11 out of the total possible outcomes. So pause the video, give that a thought, and then check your answers. Okay. So it turns out that there's 36 different possible outcomes for when you roll 2 dice. You could figure this out possibly by drawing your tree diagram. You can think after the first roll, I've got 6 possible opportunities and then 6 more out of that. That gives me 6 times 6, 36 possible outcomes. Or you might start listing out the sample space. And again, you should come up with 36 different combinations. Okay, there are 3 favorable outcomes that would lead to a sum that's greater than or equal to 11. A 5 and then a 6 and then a 5, or then a 6 and a 6. So the probability of having a roll, or that the sum of 2 rolls is greater than or equal to 11, is 0.0833. Okay. So this same type of calculation is done when we're looking at data as well. So we try and figure out how likely an event will occur in the future based on events that have occurred before. So we might look at data or survey data, and we might find that historically, out of 20,000 people surveyed, that 19,882 lived to be 31. So if we want to use that data and predict that the probability that somebody who's 30 lives to be 31 based on this data, we'd look at the ratio of the number of times that event has occurred in the past relative to the total number of surveys that were examined. And so in this case, we'd find the probability comes out to 0.9941 when we calculate that out and round to 4 decimal places. So another quick activity for you to do, looking at this table of values, try and figure out the probability that a person has type A blood, the probability that a person has type O blood, and the probability that a person does not have type O blood. Pause the video and do your calculations now. Okay, so one of the first things we want to do is double check how many people were surveyed. It does tell us 100 blood donors were selected at random, but it's always good to add up the number in the table and double check. So the probability that somebody has type A comes out to being 0.3500, probability of type O 0.2500, and then the next one's a little bit interesting. The probability that someone is not type O. So depending on how you thought about this, you may have done this several different ways. You might have thought about what all the different categories were that were not O, and then added up the probabilities related to each of those events. Or you might have intuitively said, well, the probability that something's not O would have to be 1 minus the probability that it is O. Using the results from the previous question, it comes out to 0.7500. Okay, this idea of calculating probabilities of not an event happens leads us into our first probability formula. That formula is related to complements. Okay, so a complementary event is the opposite of an event that occurred, right? So if we were looking at a particular set of data, so here we have the Red Cross data related to blood types, including Rh factor among Asian Americans. Okay, and we're asked to figure out the probability that a random Asian American has a blood type of O positive. So reading through the data, I find out there's a 39% of the population has blood type O positive. So my probability would be 0.3900. Okay, the complementary event is that a person does not have type O positive blood. And the quickest way for me to figure that out, instead of adding up the results from all of the other categories, is just to do 1 minus the probability that they have O positive blood. So 1 minus 0.3900 comes out to 0.6100. Okay. This idea also introduces a new term that I term mutually exclusive. So events that are mutually exclusive cannot occur at the same time, and an event and its complement are always mutually exclusive. Okay, it might be good to think about a few events that are not mutually exclusive, right? And so that could be that it's rainy and cloudy. It could be rainy and cloudy out. It could also be rainy and sunny, right? So the complement of a rainy day is not a sunny day, and those events are not mutually exclusive. Okay. So before we continue on, pause the video and try out the next practice of activity where you're calculating probabilities related to Canadian Blood Service data. Okay, so the first question was the probability that somebody has type AB blood, and we could realize that to calculate that, we could figure out 1 minus the probability that somebody does not have AB blood, which is the sum of the probability that they have type O, type A, or type B blood. That comes out to 0.03. The second question was the probability that they're not type O. We could look at 1 minus the probability that they have type O blood. 1 minus 0.46, it comes out to 0.54. And the next two pages of the notes now, we're going to introduce two other ways that data is sometimes organized and that we try and calculate probabilities from. So the first way that data is sometimes organized is in what's called a contingency variable or a contingency table. Contingency tables are used to display information for two variables that are often not mutually exclusive. And so when we're calculating probabilities based on this information, we have to pay close attention to exactly what population we're drawing probabilities about and where we should be drawing our sample from. So using this table, we're asked to figure out the probability that a student is female. So we're talking about any student out of the total surveyed. So the probability that a student is female, we'd look at the total number of females surveyed out of the total number of respondents. We get 46 out of 70. That probability comes out to 0.6571. Okay. The next question, we're asked to figure out the probability that any student is moving into the nursing program. So we'd have to look at the total number of students moving into the nursing program and look at it out of the total population. So the probability that a student is moving on to nursing would be 27 out of 70, which comes out to 0.3857. Okay. Third example, the probability that a student is male and moving into the nursing program. Here, we're talking about a probability that a student in general is male and moving into the nursing program. So here, we're looking at the probability that they're both male and nursing out of the total, so it would be 6 out of 70. We'd come out with a probability of 0.0857. And then I'm going to show you how the wording can change a little bit in the next one. Very similar type of question, but here we're asked the probability that they're moving in to the nursing program given that that student is male. So we're no longer looking at the total student body here. We're looking at the probability that they're nursing given that they belong to the male population identified here. So we'd be looking at nursing male out of total male population. So we'd be looking at 6 out of 24. And so that would come out to 0.2500. So again, what changed here is that we've restricted the population and we only consider the male student data in the chart. Okay. And again, the word that tipped us off there is that there was some restriction, that there was some limitation given in the question. Okay. And then the final type of way of organizing data that we want to quickly overview are Venn diagrams. So Venn diagrams are also used for displaying information for non-mutually exclusive categories. So where they're overlapping categories. And so based on a Venn diagram, if we want to know how many people were studied, we have to add up all the different values. We'd have to figure out the total belonging to all the different categories. So I'd go through and add up from each of the different categories to figure out the total number of people represented in that diagram. It comes out in this case to 102 people surveyed. And if we want to know how many people have mental health diagnoses out of that group, we'd have to look at the entire mental health diagnosis bubble. So the percent we're working with here of people who have mental health diagnosis would be the ratio of the total number. So the total number across all of the different categories, so 38 plus 14 plus 1 out of the total number of people represented, and then calculating that as a percent, it would come out to 51.96%. If we wanted to figure out the number of people or percent of people with mental health diagnosis only, well, the only person or the only one in that category is 1 out of 102 people. Everybody else has overlapping categorization, so it would come out to 0.98% of the total population surveyed. If we want to know what percent of the population has a palliative diagnosis, again, we'd go to the palliative diagnosis category and add up all of the different people in that category and calculate the percent out of the total. And for not palliative, we'd subtract that percent from 100. That wraps up our notes introducing probability. Try out the homework before moving on to the next lesson set. And if you have any questions, please don't hesitate to ask. Okay, we'll talk soon. and have a great day.